So, in the previous class we have seen the properties of electromagnetic waves, how they are created and how they transfer energy from one region to another region. So, in this class we will see that the waves can carry energy as well as momentum, and when they are absorbed by a surface then they exert radiation pressure. And next part we will see the spectrum of electromagnetic waves, that is the frequency, the wide frequency over which they vary and the wide wavelength range over which they vary, that is the visible part of that, X-ray part, radio waves, ultraviolet part and all the parts of it. So, let us see how the wave transfers momentum, electromagnetic wave transfers momentum. So, we have already seen that the energy carried out by these waves is epsilon naught E RMS whole square, or if I write intensity, that is epsilon naught C times E RMS whole square. This is the energy density expression and this is the energy carried by electromagnetic waves. Now, energy is the surrogate of all the momentums. So, if a system carries energy, the system must possess momentum. So, if my electromagnetic waves are supposed to transfer energy from one region to another, then it also carries momentum with it. Now, it can be shown mathematically that if the energy transported or energy transferred to a surface, suppose this is a surface area and radiation falls on it and the total amount of radiation falling is u, then we can show it mathematically that the momentum transferred to it, momentum transferred to it will be equal to u by c, where u is not the energy density, this is the total energy absorbed, the transferred to the system. This is the momentum transferred to the system when this energy is absorbed by this surface. So, when this surface absorbs this energy, the momentum transferred is u by c. Now, let us see the rate of transfer of momentum to a surface contributes the force. So, now we know that if a surface absorbs this energy, if this is my surface which absorbs some energy, suppose the energy absorbed is u, then the momentum transferred, let the letter we select for momentum transferred be p, small p, that becomes u by c. This is if this absorbs. Now, suppose I want to know what is the force exerted on this surface, force exerted on the surface. So, this will be equal to momentum transferred to the surface by time taken. Now, suppose u is the total energy absorbed, this is, suppose w is the energy transferred in unit time, then the momentum transferred will be this into t, that is u will be equal to that is, we will write that force will be equal to momentum transferred per unit time, that is equal to u by c into time, that will be w into t by c into t. That is, w is the amount of energy transferred per unit time. In terms of intensity, if I will write, that is intensity into area by C. That is, the force experienced will be intensity. W is the, what is W? W is the amount of energy absorbed by the surface in unit time. So W will be equal to intensity into area. So we will write force by area will be equal to I by C. This will be denoted as the pressure exerted by the radiation on this. We will call this as radiation pressure. Radiation pressure. So if this radiation is fully absorbed by this surface area, this is falling normally on it, then the pressure exerted, radiation pressure exerted will be I by C, and the momentum transferred will be U by C, where U is the total amount of energy falling. If the light is reflected by the body, then the radiation pressure becomes 2I by C, because if the light is reflected back, then again the momentum change will be 2U by C, and so the formula for this, that is the pressure, radiation pressure, becomes 2I by C. So this is the expression for radiation pressure. Thus our radiation also exerts pressure on which it falls. So now let us solve a problem on radiation pressure, and let us assume a plate like this. This is the plate on which radiation falls from this direction, and this plate is leviated because of radiation pressure. This plate has a mass m and it is hanging from a massless thread which is fixed at a point. We want to know what is the thread deflection angle theta. So its weight mg is there, and the radiation, this angle theta is so small that we can assume it nearly equal to 0. So very small angle. Now this is the force, that is radiation pressure into area. We can write it as, suppose I is the intensity of radiation, then I by C into area, since this radiation is completely absorbed. So here tension, here we can write tension T, and this assume angle this theta. So we have T cos theta balancing its weight mg, this is equation number 1, and T sin theta component as I by C into A. This is the force. Radiation pressure is I by C, it is completely absorbed. So I by C into area is the force. So from these two equations we get tan theta will be I A by C mg, where C is the velocity of light, I is the intensity of light, A is the area of cross section of this. This is the tan theta. So you see, we here use the concept that this energy when absorbed deflects this mirror or a black body by some angle theta, and this tan theta is given by this. Let us take another example. Now let us take another example where we will calculate the total force due to radiation pressure. Suppose this is the hemispherical bowl and it is completely black in the sense, it is a reflecting bowl, so it reflects light. So if a light falls here, it is reflected. So this is this is silvered I can say. Now at this center there is a point source S which emits lights in all directions. So let us calculate what is the force, radiation pressure, what is the force, net force acting on bowl, on this bowl mirror because of this surface S. So let us take an element, elemental area A, let us shade it, this area is dA and radiation falls on it, and suppose it is reflecting surface, so it recoils back. So force acting on the element due to radiation pressure is equal to 2I by C into dA. The force is along this direction. This is the direction of force. Now every element here has a counter element here. So there will be a force along this direction also. Now this force has two components, one downward and one here horizontal. So their horizontal components will cancel out, and so we will have only this component. Suppose I call this angle as theta, so we will have this component. Now you see here this dA is here, the normal to the dA, that is the force is along dF, and this is angle theta. So now we are interested in the only this component, that is dF along y axis, that will be, let us see, suppose this angle is dA, then this angle is theta, so its projection on this is going to be dA cos theta. So since we are interested in dy, I will write this as di by c, dA, let us call it dA dash, or this is okay, this is dA cos theta, so this dA cos theta. Now we want total force, so I will integrate it. So the total force on the y will be 2I by c and integral dA cos theta. Now what is dA? dA is this area and dA cos theta is the projection of this area on the horizontal plane, whose integral gives out to be Ti by c, that is pi r square, that is pi r square. So this is the total force acting on this bowl along this direction due to radiation force. This force becomes 2I by c pi r square. So thus the force which the bowl gets due to this radiation being reflected is equal to 2I by c pi r square. Let us take another problem. Now let us take another problem where I have taken a sphere, this radius r, and this is perfectly reflecting. So the whole sphere is silvered, and suppose I irradiate this, I have placed in a electromagnetic wave of intensity, and this is perfectly reflecting. So if a light falls here, it is reflected. If the light falls, it is reflected along this direction. This is normal incidence, it will get normally reflected. So in a similar manner, we can get the result that the net force acting F acting on this sphere will be equal to 2I by c. The cross sectional area will be taken into account as we have done in our previous problem. So this, in this sphere also we will get the same type of force because the same symmetricity hemisphere is there, so we will get the same problem.